Just wait for the screen to be shared. Okay, so now we are good. So yesterday already I had seen that how to apply the definition of monotonicity. Now what we can do is that we can take a problem which will illustrate the importance of it. So let's do one application sort of thing, that we are given f of x is 1 minus x cube. That's the function given. And you want to solve for all x that belong to R, and that satisfies 1 minus fx whole cube greater than f of 1 minus 5x. So let's understand the problem first. So it says that given f is this function and x belongs to R, you want to find those x's such that this greater than f of 1 minus 5x, where the symbol f of x cube is to be understood as f of x cube, although J advanced or any example, of course, write it. Now, the moment you see this function, the left side, this inequality left side, then you wonder that this has something, this resembles very much f of x, no? It's like you are getting f of x in place of x. So it makes sense to rewrite it and identify as f of x equals 1 minus f of x minus fx whole cube. So that is your f of x. If that is true, then the equation or inequality reduces to f of fx greater than f of 1 minus 5x. So it means what we have got is that we are comparing the values of f on both sides. So look at it like f of a exceeds f of b, then what can we say about a and b? In general, we can't say anything. But because nature of f is given, f itself is 1 minus x cube, so I'll differentiate with x. So f prime x, that will give me minus 1 minus 3x squared. And this number is negative. This whole thing is negative for all x belong to R. And so I can say that f is strictly decreasing. So we can say f is strictly decreasing. If it is decreasing, strictly decreasing, that means by definition that f of a greater than f of b, that means that this is equivalent to saying that a less than b. Means the sign must be turned. This was greater than, so it becomes less than. Using this idea, we are writing now this. This means that f of x, the argument is f of x, and the argument is 1 minus 5x. So f of x less than 1 minus 5x. Now we bring back our f of x, that is 1 minus x cube, and this is less than 1 minus 5x. That one cancels. I write minus x cube, and then minus 5x becomes plus. So this is plus 4x less than 0. And I can just multiply by negative 1 both sides. So x cube minus 4x is positive. I can take x common, x square minus 4 positive. And I will get x minus 2, x plus 2 greater than 0. We can draw the number line. So we have got negative of 2, 0, and 2. Sorry about that. Please note that after 2, the sign is positive. And wavy curve tells you that unless roots are repeated even number of times, they all go from alternately positive, negative, positive, negative. So positive, negative, positive, negative. And we pick out those intervals in which the sign is positive because we want it positive. And so that means that the solution becomes x belongs to minus 2, open 0, and union, this is 2, and then infinity. So that's our answer, minus 2, 0, union, 2, infinity. So that was one application based question. So this was a good application of the concept of monotonicity. Continuing further, there is one I would like to change the color maybe, in we can go with this because it's an interesting problem. So this says that find the set of all a element of R. So it means you want to find the set of all a that belong to R such that the function f of x is e to the power 2x minus a plus 1 e to the power x and plus 2x. This function is strictly it is strictly increasing it is strictly increasing for each x so for or I'll change it, so this is not needed. So for each x that belongs to R, so this I want to solve. That we are given that find the set of all a element of R, this parameter. So here a is called parameter. So this is a problem which requires you to determine the set of all values of that parameter a can take, real values of course. We are doing real calculus, such that f of x is this function e to the power 2x minus a plus 1 times e to the power x plus 2x is strictly increasing on whole of R, that is for each x that belong to R. Same way that we are applying, that we already know that if you want, f is anyway f is differentiable because f is made up of three differential functions, x, e to the power x, and e to the power 2x, and multiplied by some constant. So f is differentiable, and so we'll say that if f prime x greater than or equal to 0, that will mean that f is strictly increasing on R. Equal to 0 is fine because even if f prime is 0, it has got finitely many roots, or the important point is that these roots don't form interval. So once they don't form interval, it means f prime 0 also does not stop the function from being strictly increasing. Remember the example fx equal to x cube. There point 0 was there, but then we did not bother. So now this is strictly increasing we want. So I will take f prime x. So f prime x is 2 e to the power 2x minus a plus 1 e to the power x and plus 2. Now I want that f prime x should be greater than or equal to 0 for all x, for each x that belong to R. I want those a. It means I want to solve 2 to the power 2x minus a plus 1 times e to the power x plus 2. This is no bigger than 0, means it is greater than or equal to 0. And we want to find such a. So our question becomes, find all those a's. Find those a belong to R, for which this holds for every x, for each x that belong to R. So we can do one thing. First method I will do, that's really by basic method, but it is, and second will be much faster, but you must learn both methods. First method is try to look at it as a quadratic. So if you write e to the power x equal to t, then think that this expression is g of t is 2t square minus a plus 1, please pay special attention to it, plus 2. So gt is this function, and your problem now reduces the problem of finding all real numbers a such that this inequality is greater than or equal to 0 for each x that belong to R. That reduces to finding the set of all a that belong to R such that this function g of t, this quadratic g of t, greater than equal to 0 for each t that is positive, because e to the power x is t, and you know that e to the power x is always positive, so we will get this. So in fact, we have reformulated the problem and said that now you want all the values of a that belong to R such that this inequality holds for all t that is positive. That brings us to the chapter of quadratic equation, or location, or more precisely the topic location of roots. In location of roots, we do like this now. So we are writing that gt is 2t square minus a plus 1 times t and plus 2, and you want this greater than equal to 0 for each t, greater than 0. Anyway, this is positive, this leading coefficient is positive, and so parabola opens upwards. Now we make cases. So we make the case work on d. So first of all, if d less than or equal to 0, if d less than or equal to 0, let's calculate d first. So d is a plus 1 square minus 4 into 2 into 2. So that is a plus 1 whole square minus 16. So that is a plus 1 whole square minus 4 square, which I can write a plus 5 and a minus 3. And so if d less than or equal to 0, this case I can deal, and other case I can deal is that d is positive. If d is less than or equal to 0, then this parabola, because it has to open upwards, it will be either of this form or it will be of this form. Means either it is always positive or it is always non-negative. That is 0, it can happen when d equal to 0. This case corresponds to d equal to 0. This corresponds to d less than 0. But no matter whatever happens, the quadratic 2t squared minus this, in both cases, that will be always non-negative. So in these both cases, gt is always non-negative for each t that belong to R, each t that belong to R. So of course, in particular, so in particular, for all t, in particular, for each t that is positive. So it means in this case, we can simply say that all values will work. Now d less than equal to 0 means a plus 5 times a minus 3 less than or equal to 0. That will give me on the wavy curve, on the number line, minus 5 and 3. And so we know it's that's after it is positive. So positive, negative, positive. So we can say that in this case, all solutions of a that belong to minus 5 comma 3, this whole interval, every a from this interval works, this closed interval works. That's the one case. If I come here d positive, this is the interesting case maybe. So if d positive, I have not shown here also y-axis on the left side, not needed. I'll do the same here also. Y-axis is not shown because my interest lies only towards right. So now d positive, it means that it has two roots, call them alpha and beta. As d is positive, they are assumed to be distinct. Alpha is not beta. So your parabola looks like this. It is upwards parabola. And now notice g0. G of 0 is 2. So 0 anyway lies here. We know that 0 lies. So but 0 could lie here or 0 could lie here. We want 0 to lie here. It may also happen that 0 coincides with this. That's fine. So let's call this is beta. This is alpha. Now you have got three conditions. If you remember, this is d is positive. That is one. If you want roots like this, d positive. Second is that alpha plus beta by 2. Alpha plus beta by 2, this midpoint, this is less than 0. Even if beta is 0, that works. Even if beta is 0, which can be alpha here, 0 here. So 0 must here, because we want that this is non-negative for each t. So 0 must exceed both the roots, or at the best 0 can become beta. Means 0 can coincide with it if possible. Otherwise, no. So this is this. And third is that f of 0 that is greater than or equal to 0. Equal to 0 means it can come here also. We find, sorry about that, we are using the symbol g and not f. So I'll rewrite g0. G0 already is 2 greater than equal to 0, which is true. So this does not give any solution. alpha plus beta over 2, that gives you your a plus 1. Let's go back. So that gives you a plus 1 over 4. So that gives you a plus 1 over 4 less than 0, which means a less than -1. It's strictly less than. And then when I come to the further part, like if I come here, d greater than 0, then you will get d greater than 0. So your d was this one. Your d was a plus 5, a minus 3. So d positive will give this kind of thing. You had got minus 5 and 3, and so you have got here positive, negative, positive. So d positive means that you are saying this region, either towards this. So d is strictly positive, so this cannot be 0, so it will be open till here and here. If I take intersection of this one and this one, and of course this one, which is true for all, then we get a less than equal to -1, and this, it means -1 is here, this side. So it means I will get here a belong to minus infinity till -5, and -5 is open. So we have here case 1, here say case 2. There are no other cases. These two cases are mutually exclusive and exhaustive. And so all is left is combine the solutions. So we will say that combining, so we can say that combining first and second cases, these two cases, the answer happens to be a belongs to union of these two numbers intervals. So a belongs to minus infinity to -5 and union -5 to 3 closed. That happens a belongs to negative infinity all the way to 3. So this is your answer, that once we know this, we know that our answer is this one, to 3. So this is your answer. That's the first method that we did by simple quadratic. It's a good analysis, simple one, but it still teaches you a lot of things. Especially students who are revising their syllabus, it's really well, because that tells you the power of good old quadratic that everybody thinks they are a champion of, which may not be true. So please take care. So this is the power of good old quadratic. Next, I will do the same problem. So let me pick here this one, 2 to the power x, by other method. That will be much more simpler. So I will just copy it first. So my second solution is go like this. Now you want all such numbers a such that 2 to the power 2x minus a plus 1 e to the power x and plus 2 greater than equal to 0 for each x. I can divide by e to the power x because that is positive. So it is equivalent to finding all a equivalent, not a consequence, equivalent to the power x minus a plus 1 plus 2 over e to the power x greater than equal to 0. I can combine these two. That is 2 e to the power x plus e to the power minus x minus a plus 1 greater than equal to 0. So now I want to solve this. Now I want that tell me those a's. Though my question becomes the question I ask ourselves, that tell me those a's belong to R such that this holds for each x belong to R. Okay, so it is crucial. Solution is in two parts. First, we are saying we are getting one match. We know that e to the power x plus e to the power minus x is equal to 2. We will make use of this, but not directly, somewhat indirectly here. So we will say that because this holds for each x belong to R, this has to hold. We want this to hold. So this must, in particular, this must also hold. In particular, this must also hold for x equal to 0, say. Perfect. You can only argue that how I got the idea x equal to 0. That we will prove now. So first we are saying that, okay, let it hold for x equal to 0 also. It can hold for x equal to 1 also, 4 also. But 0 will give you the best bound. Reason will become obvious. So this is 0. So you will get, this is 4, 2 times 2. You are putting just x equal to 0 here. So x equal to 0 must hold. So a must be such that 4 minus a plus 1 greater than equal to 0. So 3 minus a greater than equal to 0. So you are saying that you got a less than equal to 3. So you are saying that all those values that satisfy this for all x belong to R. For that it must happen, it is necessary that a, this is a necessary condition, this is just we got a necessary condition, very important. By no means we have found it is sufficient, we are just saying it's a deep conceptual part, so please understand. So all we have found by some magical value that x a less than equal to 3 means necessary condition. Imagine had we put x equal to 1, say, we would have got 2. It is true for all x, so this also e plus 1 by e and minus 1 minus a less than equal to 0. You would have got a greater than equal to twice e plus 1 by e minus 1. And so in this case we could have, this is, we want greater than equal to 0, so this sign is in fact the other way around, and this is again the other way around. So these all signs must be turned. So this is, you want this, and so your a less than equal to this, you will find that this bound, this is a better bound than this one. Better means this is larger than this one. What that tells you, that in fact it is true for all, but we want set of all values. So all we know is that this is necessary condition. We will prove in second part that a less than equal to 3 is, this is the heart of the problem, is sufficient also, is sufficient also. For that what we'll do, we need to prove that if this is true, then this number, this expression 2 e to the power x plus e to the power minus x minus a plus 1 under this condition is always, this we want to prove, we have to do, then we are done. So we will write this as, so this we do not know, we are writing this as 2 e to the power x plus e to the power minus x minus a minus 1. Cleverly I will write 2 e to the power x plus e to the power minus x minus 1, because I know that, minus 2, because I know that this is non-negative. So this is plus 4, this is negative 4, so plus 4 I will have to add. So I'll have to write minus of a and plus 3. So I'll write 2 times e to the power x plus e to the power minus x minus 2 plus 3 minus a. And now we are saying, because a less than equal to 3, that's what we are saying sufficient. So this we know greater than equal to 0, because sum of a number and its reciprocal is always exceeding 2 or equal to 2, and this greater than equal to 0 by condition. So we have proved that indeed under this assumption, this is greater than equal to 0, and so we are done. We have proved both. First we found that a less than or equal to 3 was necessary, it was necessary condition, and then we also proved that in fact this becomes sufficient also. And so you will say that for all set of values, that a less than equal to 3, the inequality holds. And so this is my answer. So answer becomes equal to 3. One word of caution: suppose in this step here we want this to hold true, so someone writes this as that he wants 2 e to the power x plus e to the power minus x greater than equal to a plus 1. So e to the power x plus e to the power minus x, a plus 1 over 2. And they know that e to the power x plus this greater than equal to 2. This is also true. So somebody could have combined this and said that, see, 2 greater than equal to a plus 1 by 2. And so 4 greater than equal to a plus 1. And so 3 greater than equal to a. And so a less than equal to 3. Answer is correct, but this reasoning you must avoid like a plague. This reasoning is too bad. So this reasoning does not work. In fact, what can work, because it's like from these two you cannot say anything. From these two, it's like say call it a and call it b, still it is a, and call it c. So if you are given a greater than equal to b and a greater than equal to c, say there is a guy a whose height is, who is taller than b, and a is taller than c also, then you do not know who is taller among b and c. It may be c. So that you should not be in a rush to give this one. Sometime they may give you the answer. Of course, you can correct it by saying this way at least, that f of x greater than equal to d, where d is some parameter. You can say that if this is to hold, then then it must be true that it must hold for that x which makes x not, that x naught for which fx is small. Means the smallest value, you want fx to exceed d for all x, so it must also exceed this for its least value, then other will automatically exceed. So that you could have done that list of, that could be a good reasoning, list of f of x greater than equal to d, and we could have complete a solution by this. So please beware, it's very crucial to have the correct concept, and it is better not to get answered by wrong reasoning than to get the answer by some kind of other thing. Okay, so now let me go to some other thing, and this will tell you one exactly other kind of situation where the topic I will write like this, that this is a huge topic, so I'll do my best to cover all the things. So one is that application, so one happens that application of monotonicity, so application of monotonicity to location of roots, or to locating the roots, to locating the roots. So one application which which is always uh, asked in examinations is that how to locate roots using this application, increasing, decreasing, or monotonicity. For that, we'll start a problem that you have to you have to prove. So you have to prove in multiple choice. They will of course have some choices that this equation has. So prove x to the power 5 minus 3x minus 1 equal to 0 has a unique root, has a unique root in the interval, has a unique root in the interval, unique root in the interval 1 comma 2. You want unique root in the interval 1 comma 2. This is what you want, unique root in 1 comma 2. Now you have to prove this. So what I will do, I'll name this as f of x as usual. Name the baby first. Fx is this much. Now f of 1, if I take f of 1, if I compute f of 1, so compute the values f of 1 and f of 2, so compute f of 1, that is this one. So that number is negative 3. This value does not interest me, negative interest me, so this is less than 0. This value not important, sign important, sign is important, so you should calculate sign in exam. And f of 2 is 2 to the power 5 minus 3 into 2 minus 1. Obviously value is not important, but what important is positive, it is positive. So it is positive, you can see clearly it is positive. Now f1 is negative, f2 is positive. Okay, so if f1 is negative and f2 is positive, then we know that between 1 and 2, so on the interval 1 comma 2 open, there is some c element of 1 comma 2 such that f of c equal to 0 as f is continuous, f is continuous on 1 comma 2 closed, and this result follows from what we know as intermediate value property. I discussed it in my continuity lecture, that is called IVP short. So it is intermediate value property for continuous function. Why the name is like this, that there are other functions discontinuous, they also enjoy intermediate value property or IVP. But for all continuous function, of course it is true. For discontinuous, it's sometimes true, sometimes not true. And so we say that there are discontinuous functions that enjoy IVP. But if you talk of continuous functions, that every continuous function must have IVP. Means if function f is continuous on closed interval ab to r, and f of a equal to k1 and f of b equal to k2, and k1 may be less than k2 or k1 may be greater than k2, does not matter. Whatever it is, if there is some number, if there is something k between k1 less than k2, or k2 less than k1, depending on sign of k1 and k2 and magnitude. So if this is the case, then you will find that there is always a number x naught element of AB open such that f of x naught equals k. In other words, graphically, the separating graph, that if a function achieves a height k1 and it achieves a height k2, then it must attain every height in between. In particular, for every k, for any height k, there is some x naught such that f of x naught, the value of f at x naught equals k. There is at least one such x naught, means some x naught. There may be more than one also. So in this case, we will say it is called intermediate property, and a special application is that if one is positive, so if k1, if suppose this is negative and positive, so this was k1 is negative and this was positive, then at least once it will have the root at something, some zero will be there. You can have at least once, means you can have like this also. So the theorem just commits that there is someone, there exists x naught, or there is some number x naught, some x naught, there is at least one, at least, they're all same word, at least one x naught. So everything is same. So we say that every continuous function enjoys IVP. So here we will say that f is negative somewhere, positive somewhere, and add the word important, f is continuous. Because f is continuous, so of course between 1 and 2, in the open interval 1 and 2, there is a point c such that f of c equals 0. Okay, if that is true, then we got, till here we have got that at least one. Unique we have not got, you've got at least one root. Now the gap will be taken care of by monotonicity. So this is the function again, fx. So I will write f of x is x to the power 5 minus 3x plus 1. And if I compute f prime, my f prime x is 5x to the power 4 minus 3. And this is certainly positive for each x that belong to 1 comma 2. And so we can say that f prime is positive and implies f is, as we did earlier by definition, f is strictly increasing. So if f is strictly increasing means f can take any value at most once. Means either it takes or it does not. So f can take any value at most once. So f has already taken a value 0 at the point, this one, at the point c. Already you have got one c for which fc is 0. So we conclude from here that that's the only c, because here it tells you that in particular fx equal to anything k or fx equal to anything 0 can have at most one root. So this is at most one root. Here you got at least one root. The only way both are true is when you force that this equation fx, so this fx has, this f has exactly, so it has exactly one root in 1 comma 2, and then we are done. That exactly one root in 1 comma 2. We can also write 1 comma 2 because it does not have a root at 1. f1 is not 0, f2 is not 0. So even if you write closed interval, nothing would matter. So it means we are saying that f is exactly one real root. So let's review what I told. So I got here by IBP, I got that f has at least one root, at least one. And by monotonicity, I got that f has at most one root, at least one real root, and at most one real root. Combining these at most one, at least one, so at least one and at most one, they together force it that it has exactly one real root, and then we are done. So that's how we do this problem. It's a good one. Now let me change and do some other one based on little tricky. Now Now it is find all a belong to R such that the equation x minus sine x equal to a has a unique root in negative pi by 2 to pi by 2. It has should have a unique root. It must have a unique root in this interval minus. So this equation should have unique root. So let's do like this. You want it to be unique root. Exactly one. Unique means same thing, exactly one. Exact word is important. Exactly one. It's not a. Now, let me write the function as fx is x minus sine x minus a. So now f prime x as usual is 1 minus cos x, and this a goes, nothing contributes, derivative is 0, constant. So f prime x is this much, 1 minus cos x. We know that this is greater than or equal to 0 because cos x is always less than or equal to 1. It's of course this also is true, minus 1 less than equal to this, but this we don't need. We just need this one to conclude this. So this is cos x does not exceed 1, and so it's non-negative. We can also have this idea by this one. By half angle formula, you know 1 minus cos x is twice sine square x by 2. So that is like 2 times and sine x by 2 whole square. That's squared. You know squared is never negative. So it is always non-negative. And so this also tells you f prime is non-negative. And f prime has roots, means f prime equal to 0 has solutions cos x equal to 1, but they are all, as we discussed yesterday, they are all discrete, means they are separated, they don't form, they don't make up an interval. So roots don't make up an interval, and so even if prime is 0 does not matter. It means that this still tells you that strictly f is strictly increasing. So it means f of x equal to 0 has at most one root. It is at most one root. Let me derive the condition for at least one root. So you want the interval minus pi by 2 comma to pi by 2. So I will first write f minus pi over 2. So f minus pi over 2, that will be given by, that was x minus sine x. So this will be negative of pi by 2 minus sine of minus pi over 2 and minus a, that equals negative pi over 2. This minus comes outside. So plus sine pi over 2 minus 1 minus a. So minus pi over 2 plus 1 minus a. And f of pi over 2, that happens to be pi over 2 minus sine of pi over 2. And then we can write negative of a. So this is minus a. This number is pi by 2 minus 1 minus a. Now, if if f minus pi by 2 or f pi by 2 is 0, if this is 0, a is such, then anyway got the solution. Then we have the roots. Then we have the roots minus pi by 2 and pi by 2 for the corresponding values of a. For the corresponding values of a. So we will say that if a is such that a equal to that, these two are 0. So you are saying that a equal to 1 minus pi over 2, or from here you are saying a equal to pi by 2 minus 1. If these two are the values, then anyway function has got exactly one real root because everything is increasing. If not, then you will say by intermediate value property that f negative of pi by 2, f pi by 2, if I enforce this less than 0, means one is positive, one is negative. Of them, one number is positive, one number is negative. So it may be that this is positive, this is negative, or this is negative, this is positive, anything, possibilities. So you're saying product of this is negative, then they both must be of opposite sign, and then IVP tells you that between these two they must have a root. So it means f minus pi by 2, that I will write again, that is minus pi by 2 plus 1 minus a. So minus pi by 2 plus 1 minus a. And if pi over 2 was this one, pi by 2 minus 1 minus a. So pi by 2 minus 1 minus a less than 0. I can change the sign of a. So I can write a minus 1 plus pi by 2. And here I can write this is a plus 1 minus pi by 2 less than 0. If you notice, it's the same thing because you are writing now this way as a minus 1 minus pi by 2. So I can write like this. Let me erase this. So I can write a minus 1 minus pi by 2 and a minus pi by 2 minus 1 less than 0. And so it is clear that we have got this as pi by 2 minus 1. This is 1 minus pi over 2. So it's positive, negative, positive. And so you have obtained that this less than a less than pi by 2 minus 1. But these points also are included here. These points do work. These 2 points do work. And so in conclusion, I can write that a belongs to closed interval 1 minus pi by 2 to closed interval pi by 2 minus 1. So these are the set of all values of a for which this function has got, or this equation has got, unique root in the interval minus pi by 2 comma pi by 2 closed. So that's one thing. Let me just go to other problem. So one is this. Sometimes you are asked in exam that intervals of monotonicity. Means you have to find the interval in which the function is monotonic or monotonically increasing or monotonically decreasing, all sort of things. So one example I can take as fx is sine of fx is sine of ln x minus cos of ln x. It is given. Of course, for this to happen, x must be positive. That goes without saying. Now you want to find that all interval in which this function f is strictly increasing. So find those intervals. Find those intervals. So for that we can do quickly. So we can do in two methods. So we can do is that one is f of x is sine of ln x minus cos of ln x. So I can write here that I can take root 2 and then by the famous trick I can write 1 by root 2 sine of ln x minus 1 by root 2 cos of ln x, and root 2, this number I can write again as this one as say cos of pi over 4 sine of ln x minus sine of pi over 4 cos of ln x. That gives 1 over root 2, and sine a cos a minus cos a sine b, that is sine of a minus b. So sine of ln x minus pi over 4, and of course x is positive. Here you have used sine a cos b minus cos a sine b is sine of a minus b. So sine of a times cosine of b minus cosine of a minus sine of b is sine of a minus b. Now if this is the case, you want this is your f of x, you want strictly increasing, so take f prime. F prime is root 2 times cos of ln x minus pi over 4 times 1 over x. 1 over x. I can change this cos to sine by writing root 2 over x. That's all right. And this is sine of. So I can write sine of ln x and plus pi by 4. So if I do this, because I can write always that cos of theta is sine of 90 plus theta. So in fact, we can say that this is nothing but ln x plus pi by 4. So that is correct. And now if this is correct, then we can say that this x is always positive. I want this to be positive. So it means I want sine of ln x plus pi over 4 to be positive for all. You can include 0 also, positive you want. So if this, you want to solve this one, you want to solve sine theta greater than 0. So of course it is periodic function. So we will have that first we'll write 0. So 0 we know that it is the first and second quadrant. Sine theta is positive. So we can in fact write first 0 less than theta less than pi. But because period is 2 pi, so add multiple of 2 pi. So we can write 2n pi less than theta less than 2n plus 1 pi. So we can write our answer is this form, that 2n pi less than theta less than 2n plus pi. Applying this thing, we will get that 2n pi less than ln x plus pi over 4 less than 2n pi plus pi, because you have added 2n pi on both sides. And mind you, n element of z means n is integer. N can be any integer, negative, positive, or 0. If that is the case, I can subtract. I can write 2n pi minus pi over 4 less than ln of x less than 2n pi plus 3 pi over 4. But we want x, so we can raise to the power e, and we'll write e to the power 2n pi minus pi over 4 less than x less than e to the power 2n pi plus 3 pi over 4. And that's my answer, because you have got the x and of course an element of z. So there will be so many intervals in, and then separately on all of them the function fx is strictly increasing, strictly increasing. Let me write a second solution, and it will be more instructive. It will be more instructive as it will tell you some other aspect. So here what we do, that I consider a function f of, I'll write the symbol t. I consider a function f of t is sine t minus cos t, and I write g of t is ln of t. So two functions I define. Here t is positive, here t belongs to R. Now you want, our function is given to be sine of ln x minus cos of ln x. So this is sort of inner function. This is sort of outer function. So this is your inner function, gt, ft is outer function. We can write our function ht or hx. I can write our function hx. I can write our function h of x is f of g of x. That's perfectly fine. You can check sine ln x minus cos ln x. Now function g is strictly increasing, because gt equal to ln t is known to be strictly increasing. If you think like graph also, you'll find this kind of thing. So it means we know that this is strictly increasing, this function g. We want hx, that composition function. It is composition of f with g, composition of f with g. That's the function left side, which is same as right, because it's been named like this. So hx function is composition of f with g. G is given to strictly increasing. If you want this, then f also must be strictly increasing. That's what we want. So we'll focus on f only. But see, argument of f is now gx. So f of t, I will write f of t is sine t minus cos t. F of t is sine t minus cos t. That is one thing. Now this I can write as root 2 1 over root 2 sine t minus 1 over root 2 cos t. That is root 2 times, and we can write in terms of sine or cos we want. So you can, now sine is all right. So you can write sine of t minus pi over 4. Now f prime t will be root 2 cos of t minus pi over 4. If you want to solve this one, that this is positive, this means that this must be in this quadrant and this quadrant. So we will write that minus pi by 2 less than t minus pi by 4 less than pi by 2, and we have to add 2n pi because it is the period is 2 pi. So 2n pi minus pi over 2 less than t minus pi over 4 less than 2n pi plus pi over 2. I can bring this pi for this side, so I can get 2n pi, or so 2n pi minus pi over 4 less than t less than 2n pi plus 3 pi over 4. But remember, my t is not x, my t was ln x. So I'll write ln x less than 2n pi plus 3 pi over 4. And this is 2n pi minus pi over 4. We can raise both sides to the power e because that is increasing. So e to the power 2n pi minus pi over 4 less than x less than e to the power 2n pi plus 3 pi over 4. And that is your answer. And this perfectly matches with the earlier answer that we got. We can go back and check that this is the answer we got in the first solution, first method. We got this kind of thing. So this matches and it match. But then you notice that how we are using here composition of functions to deduce the properties of this kind of thing. And then it's really obvious that this solution is really to the point and it is shorter than the first solution, but you must master both of them. Okay, so it's time to go. So let me stop sharing now. Okay, so that's all for today.